Hi everyone, thanks for coming to this talk. Indeed, I'm a software developer at Sabre, and my company offers services and software to airline and travel industry. And most of the time we work in Java and Java-related tools, but in my department, almost exclusively, we code in C++. And I will be showing you why during the course of this talk, why Java will not do for us. And by two examples, we'll see how we make an effective, both in terms of efficiency and safety, use of C++. And if time permits, I will give you some advice. And I will be talking fast because I only have 45 minutes and lots of material. What we do in our product, what it does, is to look for flight connections and the prices. So if you are booking a flight online or via travel agency, you are probably using our software indirectly or our competitions. Sometimes there is no direct flight to where you want to go, so we will try to combine flights so that you get to your destination. But this involves a problem that falls down to operations research category. And as you know, to compute such a solution, it takes long. It may take minutes or hours to compute, but when you look for flights, you only want to wait for a couple of seconds, no more. And we are processing like thousands of these requests, so we really need to be fast. And for this reason, we apply many tricks. One of those is to cache the solutions. Usually there's the same routes that are being asked for time and again, so we will cache them. Not even at the first use, but in the morning, before the day starts, we know what the most common routes are, and we will cache them proactively. But for caching, you need memory, and memory is finite. And our success depends on how many solutions we can fit into memory, and indirectly on how much compact the solutions are. And the size of a solution depends on the language we choose. And this is how it works by illustration. Suppose an integer takes one word in memory, and I need to store two of them. So it will take two words. Now I want to wrap them in a class, because I want to talk about points, not integers anymore. So I add a class. If I compile it with C++, I get the size of two words still, because you don't need any more. If I wanted to do it in Java, and you look at the Java layout, because in Java everything is object with virtual functions, I need to have a class pointer that points me to the class representation or the virtual functions or the meta information about the class, one word. Then the mark word, because in Java every object is lockable, so I need to store a mutex somewhere. The garbage collector state of the garbage collecting algorithm, it's another word, and only then do we have the payload, the real information we want to store. So the ratio of a language overhead to the payload is 2:1. Unacceptable if we want to store lots of solutions in cache. It gets even worse when we now want to store 2 points in a rectangle. We only need 4 words for this, and this is what we get in C++. In Java, because everything is passed around by pointer, it's no thank you. And they are located in random places in memory. And it's not only about the waste of memory, but also about how efficient the access to this memory is. Accessing memory is an expensive operation at our C++ level. And we always pay for using it. So what processors do is to cache memory. They will fetch not 1 byte if you want 1 byte, but something like 64 of bytes. So if you need to make this expense, at least you get additional bytes for free. And if we want to store points in a vector, in C++, this is array of objects. They are stored contiguously. So we get these integers one after another. And in one memory load, we can get like 8 of those points. We pay for fetching one, unfortunately, the memory access, but we get a number of next points for free. In Java, if you use a vector, there is an array, but it stores pointers. And they point to random places in memory. You can only fetch like one pointer, one object. You get 2 integers. The second one is for free because it's cached. But the next memory is rubbish for our algorithm if we want to inspect all the points. And we do another memory fetch to get the second object, another memory fetch to get the third object. And there's lots of these memory reads, and we pay for this. So only for these efficiency reasons, we would not go to any JVM-related technology. But what C++ also offers to us is safety. And by safety, I mean how well it can detect our bugs before we ship the program, still at compile time. And C++ is statically typed language, so if I confuse the types, like here, I wanted to take a substring of a string, but I confused the order of arguments, and now I'm taking a substring of an integer, which is nonsense. And because types mismatch, the operations are wrong, the compiler gives me a compile time error. It's really obvious, and you may not even notice when the compiler helps you like this. Compiler doesn't know that you have confused the order of arguments. Compiler only looks at the functions, how you use them. But it's enough for us to be warned ahead of time that we have done something wrong. But it doesn't work always because C++ is very flexible. And this flexibility kills us sometimes. Like there is a handful of very useful, versatile types like pointers, doubles, integers, strings. You can do whatever you want with them, only with these 4 types. Like an integer, you can use it for representing mathematical integers or indexes in the arrays, or bit masks, enumerations, unique identifiers, and many more. At some point, you need all of these functionalities, but you never need all of it at once, but you get the interface for all of these at once. So if you have a program that uses a function that uses 2 integers, I wanted to use one as a bit mask and the other as a mathematical integer. And somehow, because normal functions are long, get lots of names, I confuse the names of the arguments. The program becomes nonsense, but from a compiler's type system perspective, it's perfectly valid. I can take a bit of an integer number, and it will not warn me. The users will warn me, or the testers. But what I can do in C++ is to use more dedicated types with a thinner interface, which only allow me to do what I need and nothing more. Now, if I use a standard bit set for operations on bits and some invented type small int for representing mathematical numbers and nothing more, and then I try to use the other's interface in place of the first one, I get a compile time error, only because I use a more dedicated types. And of course, any other strongly typed system also allows me to do the same thing. But what's particular about C++, and if we already seen this in previous slides, that I get those for free. I mean, there is some compile time overhead, some programmer's overhead for thinking what types I want to use. But at runtime, I pay no cost for it. My small int, if I implement it, will be the size of an int. Standard bit set is no more than the size of unsigned long. And we can see that this standard bit set is not perfect because it also wastes some memory for 8 bits, so I can make an even better class if I need it. And of course, this is C++, so we would offer you type safety by default, but sometimes you do want to do nasty things, and we allow you the access to the GAT. So from this small int, whatever it is, you will probably be able to get an integer and work on bits if you feel like doing it. But it will not be done accidentally. You have to request for it with a function. And this is basically how I define safety, my compiler detecting certain bugs for you, and efficiency. And now we're going through two examples of how it can be used in practice and how bugs hit you if you don't use it. The first example deals with shortcodes. Recently I was going on vacation. I bought a flight from EasyJet going from Krakow to London, Gatwick. It cost me like 1,200 Polish zloty. And even in this sentence, I used like 4 codes. Airline code, airport codes, currency codes, they're all around us. And in software, in fact, in all applications I worked with so far, we are dealing with shortcodes. So when you need to handle a shortcode, first thing that comes to your mind is which of the 4 the super versatile types I will use for representing shortcodes. Integers, not really, they are not integers. Doubles, no. Pointers, no. Strings, yes. String can handle any shortcode. So a lot of people will just use string for this purpose. And technically it works, but it doesn't come for free. If you think of it, a shortcode is nothing more than a unique identifier. I just use it to tell Poland from United Kingdom apart, but I'm never interested in Poland having this PL having first letter P. I don't care. I just check whether this identifier is different than the other identifier. It's almost as integers, except they are user-friendly because PL tells you something, and number 3 would not. But apart from that, they have nothing to do with strings. You are never interested in taking a subset of it. You are never interested in the functionality of string to grow or shrink, to handle megabytes of data. You are never accessing only the first letter. You're interested in fact, the only thing you're interested in is to copy them around and compare them against other integers. Rarely, at some point you will need to display them, so it means converting to a string. But other than that, it's only regular operations. So the string is giving us what we want, but it's also giving us too much, and that's not all. You pay with efficiency. Contemporary string implementations will never allocate memory when they know they are storing strings of arrays of 2 or 3 elements, or only those small strings. So the optimization they do is called short string optimization, and it means the string needs to be prepared for the worst case. So it has a pointer to array somewhere in memory, and its size and capacity, or some equivalent, like begin, end, and end of capacity. So we can make an optimization, and in 1 bit store the information that we are performing optimization, and the optimization is we are reinterpreting the rest of those pointers as characters. And there is no memory access or allocation anymore. And it's really good, really efficient, but not good enough for us. Because still, we are dealing with objects that are the size of 3 pointers, which may be like 24 bytes, whereas we only need 2. In order to store a 2-letter character like PL, we only need 2 bytes. If we're using 3 bytes, we are wasting memory for no good reason. Okay. And this is just efficiency. Another reason for using a dedicated type rather than just a string is safety. Suppose I have some dictionary or a map, and I put an association inside that PL represents a country called Poland. And then later on, at some point, I check whether this association exists, whether PL represents Poland, and it turns it does not. Even though, in between, you have to believe me, I didn't change the state of this dictionary. And do you know why this is the case? This is because the other function, match code, takes the code the key and the value the other way around for some reason. It may be that two different developers worked on two different parts of the interface and each of them had different intuition. Or there might have been some technical reason to do it this way. It doesn't matter because now the harm is done. You already have a bug. And contrast this with a situation if we used a dedicated type like code, which is not convertible to string and vice versa. If we do it, and if we pass the arguments the other way around, for some reason, the compiler immediately sees type mismatch and warns us. And even more, I can provide two overloads which take the arguments either way, and still the compiler, because it sees this different type, can navigate around the problem and select the correct overload, only because I use a dedicated type. So this is enough motivation to go ahead and write down your own type. And this is what we did in one of the projects I worked for. And to implement it is quite easy. The most interesting parts fit in one slide. So this code is a template because different codes may need different number of letters, like country codes can be encoded in 2 letters, airport codes in 3 letters, currency codes in 3 letters. Other codes may require more letters. So this will be parameterized, but at compile time. And in the implementation, we just use the array, like array from the standard library, which is available since C++11, or if you don't have C++11 yet, a boost array, which does the same thing. It's a row array inside, but with this STL-like interface for getting iterators and comparisons. So I do get an array and access to each element, but I will wrap it and will not expose it in the interface. In the interface, the only thing I have is the copying and moving, which I get for free because they are implicitly generated. I only need to forward the comparison operators, and I'm done. And one thing to note here, which is another safety feature, that code of 2 letters and code of 3 letters are different instantiations of a template and 2 different types. If I use one in place of the other, I get a compile time error. And note that this is not the most efficient implementation of a shortcode, but it will suffice for our talk. So that was the 90% of the interface, and then come the least interesting things, like do you want to provide a default constructor? My ideal solution would be to provide no default constructor because there is no good default country code. What should the default country code be? No good answer. But so I would ideally just wipe it out, the constructor. But if I do so, it turns out my type doesn't work with almost all the frameworks there are for communicating with the database or reading, writing XML files. Usually what these libraries do is what you do when you read the integer from input. First, you need to create an object. We don't care about its value, but we care about its address, because under this address will be fitting data. So unless I provide a default constructor, nobody will use my type. So I like it or not, I have to do it. And then because I chose to implement my code as an array, I just fill it with zeros. And then this is a bit unsafe because now I will be letting irrelevant or faulty shortcodes into my application. But I have to do it. The only thing I can provide to mitigate this problem is to give you some function like isInitialize to check whether we are storing this special state. And it will compare unequal to any other shortcode. So if you are looking for a given code, this will not match. And the harm is minimized. Not an ideal solution, but I don't think there is any good one here. Default constructors are the root of many problems. One of those is those null pointers. And of course, at some point, you have to read it from a string. And then the string either a standard string or a C-like array of characters may be too long, so I have to be prepared for handling too long size. There's a number of ways to do it. Throwing an exception is not necessarily an ideal solution. I will not go over this because we only have 45 minutes. The only point is that I'm not making it easy for you. This operation is dangerous because it may fail. So there is no constructor provided for it. You get a long name, which you would rather not type, and you always have to think before doing it and think what you want to do if the operation fails. Converting the other way to the string is easy because there will always be a string to handle your shortcode. So I would just give you if you want the C interface, you get a pointer to the first element, the size, which is a compile time constant. And sometimes you will probably want to convert a string, so you also get a function for it. But now you are risking allocating resources, so be careful, because it will cost. And the cool part about the interface with it is handling literals. It is not often that you need a literal, because usually the data comes at runtime from databases, user input. But sometimes you need some constants, like some global constants, or when you are writing unit tests. For unit tests, you only use a handful of constants. What I would ideally have is that when I'm storing a code of size 2, and I give you and I initialize with the wrong size of a literal, I want the compiler to reject my code. And this is doable in C++. It would not be doable in C, because if I want to take the array, it decays to pointer, it loses the length. And there is a problem, but in C++, I can take an array by reference with this funny syntax, n+1 elements, because those literals are arrays padded with a 0, so that you know when the literal ends. I make this constructor explicit. I will tell you why in a minute. And it will only work for the literals of a specific size. If I want to pass a too long literal, compiler gives me a message, no appropriate constructor found. It's good that I have an error message. It's bad that the error message is poor, because it may not help me identify why I have a problem. So I may address it in a different way, bind to literals of any size, but then so I have a constructor template inside the class template. And when it's matched, I reject the code later on with a static assertion, but now with the message of my choosing. And it will be easier for you to identify what the problem is and where. So what do I get with this already? If I have some function in country that checks whether the airport is located in a given country, and I check this by providing only codes, if I use strings for this purpose, and I confuse the order of arguments, to the compiler, it's fine, because they are just strings, and the program will work under some definition of working, because it will do something else than I expected. But if I use my short codes, country is code of 2 letters, airport is code of 3 letters, and I confuse the order of arguments, I get the type mismatch and a compiler error, and I have time to fix my bug before it's shipped. Thank you for this remark. Like currency code is 3 letters, and airport code is 3 letters. And then I have my problem back. The way to solve it is to introduce an artificial template parameter. I don't even need this name, because I will not be using it inside. Its only purpose is to generate more different instantiations of this template. Now I have the same size, different, look, this, I didn't even have to define this type, it's just forward declared. But it's not enough that it has a distinct name. I have 2 different types with identical interface, but they are different type. And this, in fact, implements an opaque type def, which we are lacking in C++. And this is to explain you why I want this literal constructor to be explicit. If it wasn't, and I have a function that takes two codes of the same size. Even though I use different instantiations, the conversion can work either way. And I still get the same bug as I had before. And now, because they are explicit, you are forced to give me the name of the type, and when you do it, the compiler can match them against the declaration and decide whether the code is correct or not. And this not being able to compile certain buggy programs is a feature. And as any other feature, it has to be tested. But here we encounter a problem, because normal unit tests work that you write the code, you execute it, you observe the results. But here you will not be even able to compile it, because that's the point of this feature. So what we do in Boost to test those features is to test them from outside C++. Like you will write a small program that you expect to fail to compile, run it with a test script against the compiler. If compiler reports a success, we fail the test. If the compiler reports a failure, we report the test that the test passed. To some extent, those missing parts of the interface can be tested with enable if tricks. But there is a limit to what you can do with it. Like if you use static assertions, as I did in the previous slide, the enable if will not detect it. And you will still end up with a hard compiler bug. And in practice, it turns out that sometimes you need shortcodes of variable size. Like on the cars, we encode countries with 1, 2, or 3 letters. So this template is able to address this if we add additional parameter. Now we have the lower and upper bound on the size of the literal. We have to change the implementation a bit, but it's doable with this template. Sorry. And this is for the shortcodes. And now for something I call magic values. And first we start with a bug. This is what we had in one of the applications. We are serializing an XML. And for this, we are using intermediate representation that represents elements in an XML. So there is some record that corresponds to the element, and those are attributes that will be serialized. Attributes are optional. So when we say we don't want to serialize the attribute, we put -1 in this integer, because those are supposed to represent indexes. Indexes are always positive or 0. -1 is never a good index, so we know it's special. And when it comes to serializing, we first check whether this member is -1, and if it's not, we serialize. Until at some point, somebody forgets about it, and he serializes it without any check. To the compiler, it's fine, and then we get XMLs that have negative indexes or huge positive numbers of indexes. And this was found during testing, but this is not a satisfactory solution. I would rather that my program do not go out with a bug, even for testing. The problem here, and it occurs quite often, is that we use our type to store two different kinds of information, like some proper value, like an index in our case, or information that there is no value to be stored. And we expect that the users will use it, programmer users will use it like this. First, they check whether we are storing the proper value, and only then do we use it. But the users may not know about our assumptions. And even if they do, at some point, they can simply forget it. The program is long, you get tired, you forget. So you would rather compiler also have a look at it. And if you know Boost optional, or now in C++ 17 we will have standard optional, and even before 17 most of the compilers ship already with a standard optional. This is a tool for addressing exactly this problem. Optional T is a different type than T. So if you just want to use it in place of T, you get a compiler error. And then you have to respond to it. What you will do is reorganize your code. You will probably check whether we are storing a proper value, And if so, you will extract it. But boost optional and standard optional, for that matter, are not 100% type safe because of the conversions that optional offers from T to optional T. Sometimes this expected compile time error will not occur, and the information about the potential bug will be lost. And another reason for not using boost optional is performance, because optional adds to the size of your type. If you are storing of type double, if you are storing type double, you may be storing it in 8 bytes. If you want to store optional double, you need one additional bit to say whether the optional is being stored or not. But because of how alignment rules work, it gets this one byte, because we are not storing bits normally, gets padded to the size of the biggest scalar we have, that is to this storage for double. And in the effect, the size of optional double gets doubled. And I am not complaining about boost optional, because it was designed with a different set of criteria in mind. For instance, it needs to work for any T. Our problem we have seen with indexes is a concrete problem with integers. And for a more narrower problem, we can find a more dedicated and more optimum solution. So let's go ahead and try to define it. Now we have a markable int, which means that it's like an int, but you can mark it as special, as containing the special value. We use the same implementation as before. It's okay to use -1 to represent not a number, but we should expose this information to the compiler, that is, to the type system. So markable int is a different type than int, and it's not convertible either way. But we are using int inside, so the size of our markable int is still the size of an int. We didn't add any spatial or runtime overhead to it. By default, we will construct this special value. So unless you say what value you want, you will use this marked value. We give you an explicit constructor from the proper integer value. And then when you get a compile time error at some point that you are using int instead of markable int or vice versa, you have 2 functions for checking whether we are storing a proper value and the way to extract the value. No conversions, it's an explicit function, and it has a precondition. You have to be sure that you are storing a proper value, for instance, by checking it before. But sometimes it's not the integers that we want. We also have longs, doubles. We want to work it with any type. And sometimes -1 is not a good default for a markable value, because sometimes you want to use -2013, something the minimum integer value. So let's make it a template. We like templates, don't we? So first you give us the integral type you want to store. And we will store this. And as another template argument, but this time it's not a type, it's this int. You provide it in the first place. You give us the value, like -3, 0, whatever you want. And the only change in the implementation is that we are using this special value, known at compile time. But it will only work for integers. If you want to store optional doubles, it will not work, because for these non-type template parameters, you cannot use doubles. Almost nothing except integers and pointers. So instead of you giving us the value directly, you give us the mark policy. And this policy, when requested, will generate an object with markable state. You pick it up, what it is, and you give us another function that tests whether the value we are storing is special, is this empty value. And this is how such a policy would look like. One static function that returns suppose we want to encode a marked double as -1000. We just return this -1000, and another function that checks whether it's this special value. Why do I need the 2 functions, and why would this function empty not suffice? This is because checking whether the value is empty comes for free. in terms of resource usage. Because you have an object, you only need to inspect it. Creating an empty value may require allocating resources. And this may be too expensive if we only want to inspect it. And there are other reasons, like not every type defines comparisons, or it defines like doubles, define comparisons, but comparing it to not a number does not give you what you want. And these markable types are in fact a library that you can download from GitHub, just Google for markable. And you don't even have to define your policies because it comes with a handful of predefined policies that will address 90% of your use cases, like integers with a special value, doubles that store special value as none. You can use a policy that encodes an optional bool in size of 1, in only 1 byte. Or you can encode enums, and we will use some integer value other than from outside the set of enumerations to store a markable state. And it turned out in practice that if you give us this mark policy, we can figure out the type ourselves, so you don't have to give us the T, just give us the policy. We also get the similar safety feature that two markable objects, even if they store the same T but use different markable policy, are different types that are not interconvertible. And we have the same problem if we have different types, if we want to have different types, but are using accidentally the same policy. So we solve it in the same way by providing additional template parameter. And this way, even if you have the same policy, you are able to render two different instantiations and two different types. And of course, this is C++. Sometimes you want to mess with the guts of our functions. So we also give you access to the guts if you feel you need to use it, like in serializing to the disk what you have. And you can tell the good component by how well it blends with other components in a program. So this illustrates how you can define an optional currency code with those two tools. Because neither short code knows about the markable types, nor markable library knows about short codes. So we have to glue them together, and for this we defined our policy, markable policy for storing short codes. And we are using this special empty state. Now it's the first place that it really turns out useful for representing the marked shortcode. And we have this function is initialized to check whether the value is marked. Just one instantiation, and I can use optional currency. So that's basically it. The most interesting takeaway from it is that in C++, you can employ the compiler to perform certain limited but still very useful static analysis of your code, which will prevent some bugs. It will compile those classes you declare, you will compile to exactly the same binary as if you use the raw integers, except that sometimes they will just not compile. But this is what you want. There is no runtime overhead. There are other kinds of overhead, of course, because it is your time needed to write down this class and test it. And there is a overhead at compile time, because now instantiating those templates doesn't come for free. But at least you have this trade-off where you can choose whether you want safety over compilation times. It gives you some degree of freedom. It also helps, when you think of your types like this, help you identify hidden semantics in your types. Like sometimes you are passing around in one-based indexes or zero-based indexes. Maybe you want to make it explicit and add a type like one-based index that sends a clear message that those indexes start with 1. And it's worth reiterating that you can, in fact, if you're using templates anyway, implement this opaque type def yourself by only adding another template parameter. it's not only about those bugs that come from type mismatch, it's also about you sending a clear message to everyone around, to the tools and to the fellow programmers, as to what your intentions are. And when you do so, you prevent another class of bugs which stem from miscommunication. And that's it for the talk. I'm done.